Hello there and welcome to our third video on the Unit 2 test. The third video will be dealing with page 4 of the test, which is dealing with the heating curve of water. On this axis we have the temperature. Remember that temperature is the average kinetic energy of the molecules. Kinetic energy is the energy of motion. So it's really measuring the average energy that the molecules are moving with. On this axis, we are adding heat energy. And then we have the curve going up, leveling flat, going up, leveling flat, and going up. All right. These are some true-false questions. Although it doesn't really say that, they are true-false questions. Between point A and B, kinetic energy is increasing between point A and B. Well, we see that the line is going up. A has a kinetic energy right here. B's kinetic energy is right here. So yes, the kinetic energy went up. The kinetic energy is going up anytime the temperature is going up. Between points A and B, here's points A and B, the water is melting. No, between A and B, the molecules are moving faster and faster and faster. It's not until we get to point B that the melting begins. So for a substance to melt, first of all, it starts as a solid. The solid is held together in a rigid, regular repeating pattern. Between A and B, the molecules are going faster, 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 faster. They begin moving fast, but they are staying in place. They're not going anywhere. Eventually, they are going so fast that they cannot stay in place anymore. And what happens is the molecules begin to get stretched apart because they're moving fast, and they get stretched apart so much that the intermolecular force that was holding them there in the solid is overcome, and now the molecules are free to move because you stretched them apart, and now they're free to move around each other. So between A and B, it's not melting. It doesn't start melting till we get to point B. All right, now we're looking between points B and C. Between point B, which is right here, and C, which is right here, it's melting. That is the truth. Phase changes are happening at this flat spot. Why does the curve flatten out right there? Or not curve, but why does the graph flatten out right there? A to B, once again, is making the molecules move faster, faster, faster. When the molecules get to point B, they are now moving so fast that they cannot stay together in that solid pattern. So we've got to finally overcome that intermolecular force that's holding them there. So there they are. There's the two atoms. We get them moving fast, 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 fast. They're moving so fast that they can't stay in here, but we've got to overcome that attraction between them. So from B to C, we are still adding energy. B to C, the heat energy is going into it. We are still adding energy. We are increasing it. But that energy is going to overcome the intermolecular force that was holding them there in a solid. So the length of line between B and C represents the heat of fusion. Absolutely. If you remember from Unit 1, the heat of fusion is the amount of heat energy that has to be added to get it to go from liquid, point B, to gas, which is point C. So that's what is being added right there. The length of the line BC is the heat of fusion, also called enthalpy of fusion. 55, at a pressure of 1 atmosphere, the line between B and C intersects at 0 degrees. So here's the line between B and C. We're going to bring it over to the axis, and they're asking what temperature would it be at a pressure of 1 atmosphere? Well, 1 atmosphere is the temperature that they use to list the melting and the boiling points of a substance. They call that the normal pressure. The normal pressure is 1. So at a pressure of 1, solid ice will melt or it will freeze. Liquid water will freeze at a temperature of 0. That is true. If we dramatically increase the pressure well above 1 atmosphere. We go high, we go 2, 3, 4, 5, 6 atmospheres. We keep adding more and more pressure to ice. It says the BC line would go below 0. So if this is 0 right here, the flat part at 1 atmosphere would be right along the line of 0. If we increase the pressure, they're saying that it would go down here. The line would drop. In other words, the melting point, where line B is where it starts melting, the melting point would drop. So maybe it would start melting at -3, -4 instead of 0. That is true. If you put pressure on ice, and we saw that. That was the video where the guy had a block of ice. He put a wire across it, hung weights, and the wire went right through the ice. The pressure made the ice melt at a temperature below 0. And ice is one of the rare substances that will do that, and here's why. An object responds to a change in the conditions on it by trying to lower or reduce those conditions. So when we have the molecules all lined up in ice and we put pressure on it, it's trying to squeeze those molecules closer together. So what happens? It melts. When it melts, it's now liquid. When it's a liquid, we know liquid water is less dense than the ice. When you freeze water, the water molecules all line up. The volume goes up when you freeze water, meaning the density goes down. That's why ice floats, because the density of ice is less than the density of water in the liquid state. Why is it less? It's less because the molecules are able to go closer together. So when water is in the liquid state, the molecules can go closer together, which would lower the pressure. They're now allowed to move closer together. Water is one of the weird substances that has its solid state less dense than its liquid state. All right, between C and D, the temperature of the water is increasing. So let's go up here. Between C and D, is the temperature going up? The line is sloping up. There's point C, there's point D. The temperature did go up. The average kinetic energy of the molecules went up. The molecules are moving faster, faster, faster between C and D. Between C and D, it's boiling. No, it's not boiling between C and D. C and D, it's a liquid. It doesn't start boiling till we get to D. To get it to boil, we've got to speed the molecules up really, really fast. So if we have water and we keep increasing liquid water, the molecules start zipping around very fast. Eventually, the intermolecular forces between them begin to get taxed or stretched. And then right at point D, we have to add energy to overcome that attraction between the molecules to allow the water molecule to break off into a gas form. So it is not boiling between C and D. The molecules are just going faster and faster and faster between C and D. Between C and D, the potential energy is increasing. No, between C and D, the kinetic energy is increasing. The temperature is going up. The kinetic energy is increasing. Between D and E is where potential energy will be impacted. All right, then. Now we're on to what's happening between D and E. Between D and E, the temperature is increasing. No, between D and E, the temperature is staying the same. The temperature is not going up. We are adding heat, but the temperature is not going up. What's the energy doing? Again, the liquid molecules are flying around each other, but they are still being held together. What's happening with the energy between D and E is it's adding the energy to overcome that attraction and allow the gas molecules to break off and fly as a gas. Between D and E, the potential energy is increasing. Absolutely. We are adding energy in between D and E. We are still adding energy. The energy is going up. The temperature is not going up. So the kinetic energy is not increasing. The potential energy must be increasing. If the kinetic energy is not going up, then the potential is going up. Why? Why is the potential energy going up? Because we've overcome the attraction between the water molecules. The water molecules in liquid state are attracted to each other. In fact, very strong. That's why liquid molecules are together more closely in the liquid state than in the solid state. We overcome that attraction. That attraction's still there, but we've separated them. If we get those molecules back closer together, that attraction will pull them together, releasing the potential energy. So D and E, the energy is going up. What kind of energy? Potential, because we're stretching those molecules apart. It's like stretching a spring. When you pull those water molecules apart and make them go gas, it's like a spring that's been stretched, and later it can pull them together again. The length of the line between D and E is the heat of vaporization. That is true. Heat of vaporization is the energy you have to add to overcome the intermolecular forces holding the molecules together. (62) At 1 atmosphere, that's the normal pressure. That's what all the temperatures of the phase changes are based upon. It would intersect the graph at 100 Celsius. Well, if we take this line and go straight over to the graph, at 1 atmosphere, it would be 100 Celsius. At other pressures, other than 1 atmosphere, it would change where it intersects the graph, as the next question leads us to conclude. If we increase the pressure to 4 atmospheres, D and E would be below 100. So they're saying that if we increase the pressure, the boiling point would drop down below 100. Oh, no, 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 no. If you increase the pressure, the boiling point would actually go up. So if we increase the pressure, D would be up here somewhere. So this line would keep going up, 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 up to up here, and then it would flatten out. Why would the boiling point go up when the pressure goes up? Well, we have water as a liquid. If you have a lot of atmosphere pushing down on that liquid, it makes it hard for the water molecules to break off and go into gas. So the molecules at the surface of the water are trying to go up, but the gas above it keeps pushing them together. It holds it down. It doesn't begin boiling till the two pressures are equal. The pressure of the boiling is trying to push the molecules out. The pressure of the atmosphere above it, the vapor pressure above it, are trying to push them down. When they're equal, the molecules can escape. When the pressure is higher than the pressure of the water pushing out, it can't boil. When the pressure above it is less than the pressure of it, that's when they shoot out. All right. So at a pressure of 4 atmospheres, the line would be higher up. As we said, this line right here, DE, would be up higher. Between D and E, the water is boiling. Absolutely. Between D and E, the water is boiling. Between E and F, the vapor, water vapor, the temperature of the water vapor is increasing. Yep, E and F, the line's still going up. Between E and F, the line's going up. So they're traveling faster, faster, faster. The kinetic energy's higher. Between E and F, it's boiling. No, between E and F, it's not boiling. Between D and E, it's boiling. Once it reaches E, they are all in gas state. It's no longer boiling. It's all a gas. Here we go. Which one of the following statements is false? Which one of the following statements is false? Moving from E back to D, condensation is occurring. E back to D, condensation is occurring. True. D and E, it's going from liquid to gas. E to D, it's going back. B, moving from C to B, freezing is occurring, illustrating an endothermic process. Well, we'll pick up with question 68 on our next video.